Hello, I'm Mr. Shrum, and I'm back again with this mastery test walkthrough tutorial um, homework walkthrough thing. Yeah, I forgot what I call these, but anyway, we're here. We're learning about Newton's first law, also called the law of inertia. And if you recall what that means, it's that objects want to continue doing whatever they're currently doing. If an object is at rest, it wants to stay at rest. If it's moving at a constant speed in a straight line, it wants to continue moving at a constant speed in a straight line. Okay? So let's take a look at some of these questions and see how we can apply that. In the first question, we have a 10-kilogram box, and it's at static equilibrium. Static equilibrium means that it is at rest, and the sum of all forces acting on it, external forces, equals 0. So we have the gravity force pulling downward, and that force is equal to 98 newtons. What is the minimum force that would be required to just pick up the box? Well, since 98 newtons is pulling it downward, here we go. You would need more than 98 newtons to move it. Because if it's just 98 newtons, then that would still be equilibrium. But you actually want to move the box. So that force will have to be greater than 98 newtons to move it. And in the upward direction. Okay. An object of mass 5 kilograms is moving across a surface in a straight line with a speed of 3.5 meters per second. What amount of force would be required to keep the object in motion if you ignore the surface friction? So like the last problem, it's in equilibrium, but not static equilibrium. This time we have an object in dynamic equilibrium. So we'll have this object, mass of 5 kilograms, moving this way in a straight line at 3.5 meters per second. And if we're ignoring surface friction, that's important to remember. Ignore friction. Okay, and then I'll stop sharing. So this object was in static equilibrium and wanted to stay at rest, but now this object is moving in a straight line at a constant speed, and we're ignoring friction, then it's in dynamic equilibrium. So this object wants to continue moving in this way. So it will not take you any force to make it continue doing this motion. So the answer is 0 newtons. If it's in equilibrium, you do not need to have an external force acting on it to make it continue going in that direction. Okay, so the answer is 0. A car is moving at a constant speed along a straight line. So that That phrase is a red flag for dynamic equilibrium. Moving at a constant speed along a straight line, which statement is true about the forces acting on the car? Well, the net forces acting on the car from all directions is 0. And another way to write that out for 3. Object moving in a straight line at constant speed equals dynamic equilibrium meaning the sum of all external forces acting on the object equals 0. Okay? Anytime you've seen this phrase, think dynamic equilibrium, sum of all forces acting on it are 0. Or the sum is 0. Okay. Let's move on. Number 4. So we have a force of 20 newtons exerted on a chair from its right and a force of 12 newtons applied from its left. What is the net force acting on the chair? And in what direction will the chair tend to move? Okay, so let's draw this out. If you're ever confused in physical science, let's draw it out. And we're going to draw a type of free body diagram, or an FBD. And that's just mapping out the forces and in which direction they're going so you can more easily understand what's happening. So we have 20 Newton force from its right. And then 12 Newton force from the left. Okay, here we go. Free body diagram. Here's the object. There's a force coming from the right and a force coming from the left. Okay. Another way to draw this out. $20 newtons going to the left, 12 newtons going to the right. And so now we're just subtracting. So if 20 newtons are going this way and 12 are going that way, 20 minus 12, 20 minus 12 equals 8 newtons. So the remaining force is 8 newtons, and it will be moving towards the left because the force applied from the right to the left is more than the force going the other way. Okay? Does that make intuitive sense to you? I hope it does. And all you need to do is practice with this. Reading questions, drawing a diagram of the forces, and then subtracting the forces to see which way the object will tend to move. L, or Ellie, I think L. L is playing with a ball in a bus that moves in a straight line with constant velocity. There's that phrase again. So think dynamic equilibrium. What can you say about the motion of the ball in the moving bus if L throws the ball vertically upwards? Well, the ball will fall back to L. right? So in the lesson, in the tutorial for Newton's first law, we talk about being on a moving bus or a moving car. And when you stop the car, you kind of lurch forward. But then when you're stopped and then the car moves forward, your body moves backwards, right? So that's your body wanting to stay doing whatever it's doing. Your body has inertia, the car has inertia, and there are competing inertias at play. So if L is in a bus, it's a very sloppy bus. Bam, bus. If you can't tell it's a bus, now you can. It's a bus. So if this bus is in dynamic equilibrium, and then within that bus, you have L. Throw a ball up into the air. So picture we're inside the bus now. Bus is moving, and then L throws the ball into the air. Well, the movement of the bus will be competing with the inertia of the ball. The ball wants to continue doing whatever it's doing, but so does the bus. So when the ball reaches into the air, the bus is moving forward. And so that ball is going to stay in this place, but the bus will be moving forward. So to L, the ball will appear to be moving backwards. Okay, it will fall. L will move forward with the bus, but the ball will not. And that will make it appear as if the ball is falling backwards, okay? And you should try it next time. Next time you're in a car, throw something into the air safely, of course, in the back seat, and see what happens to the object. A lot of this physics stuff makes intuitive sense. Like if you go and try it, you may know what I'm talking about, but now you're learning to explain why this occurs in such a way. And that's the cool part about physics and physical science. Okay, next question, number 6. 2 bricks, A and B. So we have an A brick and a B brick, the brick. They're kept on a table. Brick A is heavier than brick B. What can you say about the inertia of both of the bricks? Well, okay. So let's see. A heavier, which tends to mean brick A is, or we'll say has. Brick A has more mass than brick B. And more mass more inertia. So the more massive an object is, the more force it's going to require to move it if it's stationary, or stop it if it's in dynamic equilibrium. Okay? More mass, more inertia. So brick A is larger than the inertia of brick B. Next question. If a hockey puck is made to slide along a straight line on a completely frictionless surface, which statement about the motion of the hockey puck is true? Well, once again, this phrase is dynamic equilibrium, straight line, frictionless surface. The puck will continue moving with constant velocity along a straight line because it's in dynamic equilibrium. 8. A car weighing 10,000 newtons is parked in a garage. Which statement is true about the forces acting on the car? So it's parked. That's static equilibrium. And the net force acting on the car from all directions equals 0. So the last one was, number 7 was dynamic equilibrium. Number 8 is static equilibrium. The net force acting on it is 0, or the sum of all external forces equals 0. That's 2 ways to write it. Now we're given free body diagrams. Which diagram represents an object at static equilibrium? So an object at static equilibrium, all the forces have to cancel each other out, right? If this force is going down, there has to be an equal and opposite force in the opposite direction, okay? B, there's no opposing force for this 20 newtons, so that's not the answer. Let's check out C. Force going down is 50, force moving up is 50, so that's good in the up and down direction. But from left to right, the forces don't add up, so they are not in equilibrium. So B and C are out. Then we look at D, same thing. None of the forces cancel each other out. D is not the answer. A is the answer. The force going down equals 50. The force going up is 50. So that equals each other. And then from left to right, 20 equals 20. So that is the one in static equilibrium. And then lastly, we have 10. The first law, in the absence of an unbalanced force, an object at rest will stay at rest, and an object in motion will stay in motion. Okay, that's the key law, the law of inertia. The law of inertia. So think of inertia whenever an object is at rest. They want to stay at rest. An object in motion will stay in motion. That is the first law of Newton's. So that's it for today. I hope that was relatively easy to understand, and I hope I helped you out with that mastery test. And I will see you guys next time. I hope you have a wonderful day / week / break, whenever you're doing this, but I'll see you guys later.